So hello and welcome to my talk, Breaking Windows with Your ARM. I'll start with a few words about myself. My name is Rotem Salinas, and I'm a security researcher in CyberArk's research labs. My work focuses on vulnerability research, malware research, and my expertise is reverse engineering and malware analysis. I previously spoke at conferences such as RSA, BSides Las Vegas, and Digital Crimes Consortium. And in my free time, I enjoy playing the drums. You may follow me on Twitter as well. So our agenda today is a short introduction of the subject. Then we'll dive right into some Windows on ARM internals primer. Then we'll see some kernel mode rootkit techniques. And finally, we'll close with some takeaways and questions. So what is ARM exactly? ARM is all around us. Devices such as smart TVs, phones, tablets, Raspberry Pis, and most recently even laptops and desktop computers are all running on ARM. But what is it? So ARM is a specification for processors based on the RISC or reduced instruction set computer architecture, as opposed to Intel's processors that are based on CISC, compound instruction set computer architecture. The main difference between RISC and CISC architectures is that in a RISC architecture, every opcode has a fixed byte length, while in CISC architecture, each opcode has a different or variable byte length. ARM has become very popular due to the low energy consumption and great performance, and lately more popular than ever since the introduction of the M-series chips or Apple Silicon as we know it. Windows on ARM existed under many names in the past, including Windows CE, Windows RT, Windows Phone, and Windows 10 Mobile. And its latest incarnation is Windows 11 on ARM, or actually Windows 11 on ARM 64. Microsoft has launched several devices to use this platform, including the Windows 11 on ARM 2023 Dev Kit and the Surface Pro laptops to encourage users and developers to adopt this technology. And other vendors are also catching on to this, including Lenovo, Samsung, and HP. So in this presentation, I will talk about rootkits on the Windows on ARM platform, which brings us to what is a rootkit exactly. So a rootkit is a type of malware that hides itself in order to evade detection, specifically by subverting the OS and while hiding inside it, typically living in the kernel space. And the term rootkit is taken from the Unix terminology where root is the most privileged user on the system. Now, rootkits are usually divided into two basic types based on their privilege level: kernel mode rootkits and user mode rootkits. Kernel mode rootkits are the typical rootkits. They run as a highly privileged user, such as NT040 system in Windows, in the kernel itself, and can modify kernel structures in memory, which they do in order to manipulate the OS while hiding inside it. In Windows, this would typically mean running as a kernel driver. User mode rootkits, on the other hand, do not have a kernel mode component and would hide their presence on the system by using user mode techniques and APIs that manipulate the OS, such as hooking and process injections. These days, many modern malware families contain some form of a user mode rootkit component, as they usually do try to evade detection as well. In this presentation, I'm going to focus on kernel mode rootkits. So in order to begin this research, I purchased a Windows on ARM 2023 Dev Kit, which comes pre-installed with a fully patched Windows 11. And my goal was to see if I was able to find any techniques that can be that can be used for rootkits on such a system, and obviously write a POC. I also had a few assumptions made. Secure boot is off, and both KPP, kernel patch protection, aka patch guard, and DSE, digital sign-in enforcement, are off, which basically means I had a kernel debugger attached to the system. And I will expand about these mitigations later on. The reason I made these assumptions is that bypassing these mitigations is a whole different idea than developing rootkit techniques, and hence it was out of context. The rootkit techniques I will describe can be applied given the mitigations have been bypassed. And finally, I had another goal, which was once I discovered how to create hooks, etc., on the system, to write a tool to detect these techniques. And the tool I wrote was released on GitHub last year. Okay, so at this point, let's jump right into some Windows internals primer for Windows on ARM. So Windows on ARM, like any Windows OS, is divided into user space and kernel space. Unlike x86-64, which has only 2 privilege levels used, ring 0 and ring 3, ARM64 has 4 exception levels called EL0, EL1, EL2, and EL3, which stand for user mode, kernel mode, hypervisor, and secure monitor. And in order to escalate to a higher exception level, one would have to use one of the following instructions: SVC, HVC, or SMC, depending on the current exception level. So in order to understand how user mode to kernel mode transition on Windows on ARM works, let's take a look at some example. So here we have our application, app.exe, that needs to open a file from disk. It uses kernel 32 API functions such as create file. Then when create file is invoked, the implementation that resides in kernel 32 will parse the parameters passed to it and will call the undocumented anti-create file in NTDLL. And basically, up to this point, everything we saw is just like x86-64, but how do we transition to kernel mode? So by taking a look at the disassembly or implementation of anti-create file, which is located in NTDLL, still in user mode, we can see that it is implemented by using only 2 instructions, SVC and ret. And basically, the OS maintains a table of handlers known as KI ARM64 exception vectors, where its base address is stored in a special register called the vbar EL1. And each table entry is aligned to hex 200, and when an exception happens, the CPU will immediately execute some code at some offset of the vector table. For instance, when SVC is executed, a special trap is triggered, which will transition to offset hex 400 in the table, which is KI user exception handler. The final part would be that KI system service would eventually be called and will take the syscall number that was passed to the SVC instruction as an index to the SSDT table, which will translate the value found in that index to the handler function for that specific syscall using a special formula, which I will explain later. Once that is done, the appropriate kernel version of anti-create file, also can be referred as ZW-create file located in NTOS kernel, will be called, which will do most of the work. And the appropriate disk driver will do the actual reading from disk. So please remember this example when I will talk about some of the rootkit techniques, because this user mode to kernel mode switch provides us with several options to hook syscalls in order to manipulate or tamper past arguments and return values of this mechanism. And as I promised, here are some of the mitigations I purposely disabled by using the debugging enabled boot option and attaching a kernel debugger. So PatchGuard, or KPP, kernel patch protection, is a mechanism that protects kernel structures from being changed in memory or patched by an attacker. It periodically checks each kernel structure for changes or inconsistencies, and if it finds that a change was done, it would cause the system to blue screen with a bug check such as critical structure corruption or kernel security check failure. You can see a list of inconsistencies in the right, and as you can see, there aren't a few, and probably you can't read it, but there's really many of them. This is also a good time to mention that PatchGuard kicks in undisclosed intervals of between 15 to 30 minutes which leaves plenty of time for an attacker to revert his changes before risking of getting a blue screen. DSE, or driver signature enforcement, is basically checking that a driver is signed by a trusted certificate before loading it. And finally, most recently, Microsoft introduced a blacklist known as the a blacklist of known to be vulnerable drivers that are not allowed to be loaded. This mechanism, when enforced, is basically checking if the hash of the currently loaded driver is in the blacklist. And this is basically to prevent bring your own vulnerable driver attacks. So now, let's see some kernel mode rootkit techniques. So in this research, I implemented 3 techniques: DCOM, SSDT hooking, and a global hook in the KI system service. And this is a good time also to say a disclaimer that these techniques are not stable, and PatchGuard would BSOD on most of them. So the first technique I'm about to show was the easiest to find, as it is pretty similar to XE86-64. The only difference is in the offsets used in the code, since the relevant kernel structures are different. The theory behind this technique, and the example I will show here, is that an eProcess object contains a linked list of all the active processes in the system, called the active process links, where each link is also an eProcess. And by looking for a specific process name in the image file name field, we can find our target process in the list, and once we find it, unlink it from the list. Now, throughout the demos, I will be using a tool, which is basically a version of the detection tool I released with some extra features, such as sending octals, hooking, etc. And I will be using it during the demos, but don't worry, I will explain everything you need to know about it. So let's continue. So to our demo. So basically in this demo, I'll start Task Manager. And next I will start also Notepad. And as you can see, Notepad has an entry in the task list. And then I'll open my special tool. I'll start a driver, and I'll send a special ioctal. And now Notepad is gone from the process list. Although the process is still active, we can see it clearly, the window. And even if we look for the window in Process Explorer, it will say that it is unable to find the Windows owning process in the current process list. Okay, so that was pretty cool. Now, before we go ahead with the next technique, we should talk about the concept of trampolines as an intro. In assembly, a trampoline is a piece of code whose sole purpose is to jump to some memory address. In ARM, as opposed to Intel architecture, it is not possible to jump to an absolute address using a single instruction, such as a far jump. So in order to do that, actually we need 3 opcodes. The first opcode assigns a register with the page address of our target address. The second opcode adds the offset within the page to the same register, which is basically the 12 least significant bits. And the third opcode jumps to the address stored in the same register. And that brings us to our second technique, which is SSDT hooking. But first, what is the SSDT? The SSDT is a table whose purpose is to store function pointers that are used as handlers for different syscalls according to their index. In 64-bit versions of Windows, the use of function pointers was changed to an encoded D word called a compact offset. A compact offset is basically a value that can be decoded into a function pointer by shifting the value left by 4 bits and adding the base address of the SSDT table. So in order to hook this table, we would need to overwrite a value in a specific index, which is a compact offset, with our own specially crafted compact offset. that encodes a function pointer to our hook function. Our hook function will execute some malicious code, and then we'll jump back to the original syscall handler function, which we will get by decoding the original compact offset. So to illustrate, I made a nice diagram. So this is basically how a proper SSDT table looks like, where in index 55, hex 55, it contains a compact offset that can be decoded using the formula to Entos kernel version of ntcreate file. So by hooking the table, we will basically override this value in index 55. The new compact offset will be decoded given the same formula to an address that points to an attacker-controlled code, and it will make some manipulation to the function's arguments, and then we'll jump to the original syscall handler function. And this is done basically in order so the syscall will actually be handled and the user will not notice anything wrong. So in theory, everything works, but in real life, I stumbled upon some challenges. The first challenge is that when I tried to overwrite the index value in the SSDT table, I found that the memory is flagged as read-only in the kernel. So a trick I knew existed in x86-64 Windows was basically that we could flip a single bit in CR0 to disable the kernel write protection, but that couldn't work on ARM. Well, eventually I found that by using MDLs, I can create a mapping of the same memory with different permissions, and then write to that MDL, which surprisingly worked. And I call this function super copy memory. And before the next slide, I should introduce another concept called code caves. So a code cave is an executable memory space in the process address space that contains either null bytes, unimported instructions, or such as breakpoints, NOPs, or other uninitialized data, and can be overwritten without disrupting the operation of the original binary. So the second hurdle I stumbled upon was when I overwrote the compact offset. I had to replace it with another compact offset that will decode using the formula to an address of some executable memory controlled by me, or a code cave, where I could write my hook code and the tuple in back to the original syscall handler function address, decoded from the original compact offset. This means that I had a double constraint. I had to have executable memory, and the memory address has to be relatively higher than the SSDT table's base address, but not too far off, so the compact offset will not overflow the DWORD size. The trivial solution was to allocate some executable memory using exallocate pull-with tag and hope that the address will fit in terms of being relative to the SSDT table's base address window, so the formula would work, but obviously it didn't work. And the actual solution was scanning all loaded drivers in the kernel for a code cave pattern, which consisted of 2 NOPs, which are 8 bytes in ARM64 architecture, followed by 16 null bytes. This guaranteed that the memory is surely executable, both executable and contained unused code, hence it is executable and can be overwritten using the method from challenge 1. And the final step was to check that the specially crafted compact offset encoded from the address can be decoded successfully, and then writing the hook and overriding the SSDT entry. So let's see a demo of that. So here we have a kernel debugger, and we just broke the kernel debugger. And I'm looking at a specific syscall handler for anti-add atom, which is in entry hex 47. Then I will use my tool to get all the syscalls and look at the code there. And I will look for the entry, which is the 71, number 71, which is hex 47. And we can see that it's unchanged. It's basically the original handler. Nothing was done to it. Next, I will put the index 47 and I will hook the SSDT. And we'll take a second look at the syscalls. Again, entry 71, and here we can see a trampoline. So let's investigate a bit in the kernel debugger. So looking again at that same entry in hex 47, we can see our trampoline, and we can follow the trampoline and see where it jumps to. So I took the page offset and I added it to the original offset, and we got anti-add atom. So this is a quick POC that I did, and basically the fact that we didn't crash means that it worked. The third and last technique I found started as an attempt to find something similar to an MSR hook on Windows on ARM. I began trying to override the vbar EL1 register that points to KI ARM's exception handler vectors table, but unfortunately I was not able to make this technique work except for making the machine unresponsive. But after some thinking, I was able to get the same effect by hooking KI system service, effectively achieving a global hook for all syscalls. So basically on the left we have the original KI system service, and what we're going to do is basically overwrite the first 3 instructions with our trampoline, which will jump to our hook. Then we have the first 3 instructions that we overwritten, our malicious code, and the second trampoline to jump back to the 4th instruction. So let's see a demo of that. So again, we have the kernel debugger. And let's look at the KI system service handler. And as we can see, it's unchanged. It's not hooked yet. Okay, let's go back to our machine and open our special tool. We start our driver, and let's investigate a bit. So we have the vbar EL1 address. Let's look at it and see that it actually points to our KI ARM64 exception vectors, and hex 200 from that would be KI kernel exception handler, and 400 from that would be KI user exception handler. Going back to our tool, we will hook the system service handler now. And again, we didn't crash, so it means it worked. We are breaking again to investigate. So let's look at the KI system service handler. So we can see that the first 3 instructions were replaced by our trampoline. And basically, if we follow the trampoline with the offset and the page address, we can see that we have the first 3 instructions that we overwritten, and a second trampoline back. Which we'll just validate. And yeah, it's the 4th instruction. Okay. So thank you for bearing with me that far in the talk. So all the information I just talked about was released in a blog in CyberArk's threat research blog, and also the tool to check for or detect these techniques. And let's have some takeaways. So IR teams and malware analysts should prepare themselves for a new surge of malware and rootkits targeting ARM and ARM64. Security operations center teams and sysadmins should monitor and check mitigations such as secure boot, patch guard, and driver signature verification enforcement that they're turned on for all users and machines. And it is not recommended for users to install third-party drivers from unverified sources. Even if signed, they might contain bugs or vulnerabilities that might allow attackers to tamper with the system. And yeah, that's it. If you have any questions.
Thank you.